So, hi everyone, welcome to the class today. Let's start maybe with a reminder of what we discussed in the last lecture. The last lecture was a lecture about SDN switches, and we saw a lot the hardware, what is the internal of the switches. We saw this at different levels of detail, different levels of abstraction, and we got some better understanding of how switches work, and also what are the challenges for SDN in the context of switches, because as if you remember, we said that the switches are not that simple. They don't have just a simple flow table. They have a pipeline of cables, and these tables are aware of IP addresses, they're aware of MAC addresses, of established protocols, and this is perplexes the idea of getting rid of standard protocols and evolving networks, which was one of the maybe let's say goals of SDN and OpenFlow. Okay, now we got some better understanding of the hardware, and today in this lecture we will move a little bit up, and we will go to controllers. But before talking a lot about controllers, today we will do two more things. The first thing is that we will watch together a video which is about an 9-minute video of a speaker. This speaker is a very well-known person. It's Nick McHugh, and he's the person who is considered as the father of software-defined networking, and who, along with other people before him, developed this branch. And I think it is worth to see a little bit of Nick McHugh. Nick McHugh has been extremely effective in explaining the value of SDN, especially to the industry, and he's very charismatic as a speaker, and some of the success of SDN and the adoption of this technology in the context of computer networks after many years, it's due to him. So I think it's important to see a little bit of Nick McHugh, 9 minutes of him. And I picked a video, it's a 2014 video, from a lecture he gave about software and the importance of software. In this video, he will discuss some of the trends in computer networks, and the importance of software. So we will start with it. And on the way, I will try to pause, since I'm sure you might not understand everything, and therefore I'll pause the video in a couple of points so that we can also discuss what he is talking about. So this will be one of the things we will see today, and I think it's very interesting about this lecture that he talks a bit. Second, today we will talk about the concept of abstractions. So when we are talking about software, it's very important to understand the concept of abstraction. And we will discuss this, and we'll explain what it is and why it is important, and we will use this to also understand what software-defined networking. We will connect the concept of abstraction with software-defined networks. I believe that these two will cover more than half of the lecture today, these two things. And finally, the third thing, we will do an overview of some of the most important controllers that exist today in the arena of software-defined networks. Okay, so without further delay, let's start with this video. In the beginning of the video, the picture might not be, the quality might not be very good, but it improves on the way. So if you are not able to read everything, don't worry, just try to focus on what he is saying, okay? And don't worry if you don't understand everything.
It's coming. Pretty interesting set of events taking place now, and that's what I wanted to talk about today. One or two of you have heard me talk about this before, so I apologize if there's a bit of a repeat. But I'm really to actually do anything, so now I try and think about what other people are doing. So this is a little bit of a step back and say, what is actually going on right now? So I think there's a bunch of trends that a lot of us are familiar with, and I'm just trying to sort of put them together in one place. Because I think it explains a lot of what's happening with SDN and NFV. There's three things that are extremely relevant to the discussion today. One is clearly the rise of open source software. The second is rise of merchant switching chips. And rise of merchant switching chips is pretty important part of this whole SDN change and movement. And the third one, which is really the driver, the need for operators to reduce cost and differentiate the service that they provide. So let's take a look at software in 2014. I'm going to say something that you all know, but I'm going to put it here in one slide. And it's really quite revealing, I think. So 75% of smartphones that are sold today are based on an open source operating system. We all know that, Android, right? About 2/3 of all web browsers that are in use today, or rather 2/3 of use of web browsers, is for open source browser. About 2/3 of websites are based on open source software. Data center servers, about 70%, probably a little bit higher than that, are based on open source software. Tablets that are sold, about 2/3. Mainframes, about 2/3. Who would have thought that, right? Supercomputers, all supercomputers except one apparently, are based on open source software. And all of these numbers are still growing to the extent that they can. And it's quite a remarkable change, because if you just track these numbers over the last few years, obviously there's been a huge change. And what is it that they're using the open source for? It's for pieces of infrastructure that are necessary but non-differentiated. Right? In all of these cases, it's pieces of infrastructure that are necessary but non-differentiated. Okay. And you get all the benefit of everybody else doing the QA for you and the development. It's more agile, reliable, and secure, but it's used where essential but non-differentiated. Right? This is part of you will have this statement before. But it's worth thinking about what this means for what we're doing here. It means that over time, and I couldn't tell you whether this is 1 year, 5 years, 10 years, all of the essential but non-differentiating parts of the infrastructure, and what is the network? Its infrastructure will be open source, right? And that's why we're here today, and why there are so many open source projects going on in networking. Let's have a look at the second one, the merchant switching. So this is a bare metal switch. There are many types of, let's just call them generically low-cost switches. They may be bare metal, they may have a logo on it. It doesn't particularly matter for this discussion. And what do they have inside? The CPU, not dissimilar to the one in the servers. DRAM, the same as in the servers, and the power supply and the fan is pretty much the same. And then they have a switching chip sitting next to it. This is an example of one of them. And then the whole thing is put in sheet metal, and then it typically runs Linux. I remember being laughed out of the room about 10 years ago when suggesting that networking equipment should be running Linux. Right? Now you would almost not think of using anything else, right? It really is changing very fast for the switches. And it doesn't matter whether it's a logoed switch or an unlogoed switch. This is pretty much what's happening. And the way in which this is developing on the switch itself, programmable hardware, open source, the necessary, the essential, but non-differentiating part of the system, and then the proprietary software that sits on top, either to differentiate that box from something else, or sitting off the box if that's being remotely controlled. And it's happening really fast. You've probably all seen this picture of the OCP wedge switch with the Broadcom Trident 2 switch in here. And there's kind of nothing in there, right? It's programmable hardware. You can't see the open source. Right? So this again, whether that's sold with a logo on it doesn't particularly matter. These two things are going hand in hand because it's becoming possible to load that software on something from somewhere else. Right? So you can buy on, and we're seeing this with bright boxes, with all sorts of stuff, the sort of the disaggregation that's taking place. And if you look at the various pieces of software that are coming out, since OCP networking started last year, we've seen lots of things. Bootloader that you can now get. Oni. The open source, kind of getting there, the open source API and drivers with OFTPA. There are alternatives to this as the Linux running on the box. All of these designed together. A forwarding agent, there are several that are available. I've forgotten. Various types of open source forwarding agent or in the process of being made open. Then an optional remote API to a network control plane, what we're thinking about here. Choices, ONOS ODL, various other types of open source. Again, my apologies if I've forgotten any there. But all of these and it's not that we've just been looking and now we've seen them. If you think about the rate of creation, the rate of availability, the number of people that are involved in developing this, 3 or 4 years ago, it was almost impossible to find anybody who would risk spending their time on open source software for networking. It was a real struggle to find anybody that would do that. Now, it's like what we're all doing, right? It's what everyone is doing, because you can see the necessity for that essential but non-differentiating piece. What it means for those who operate and node networks is the creation of those rather boxes at the top. Of course, it's more complicated. They're the differentiating pieces of proprietary software. And if anything, the biggest challenge that comes out of this is not the pieces here, because they're shaping up. The hard part is figuring out what are those proprietary differentiating use cases and services that will be created on top. Luckily, for most of us, that's left for those that own and operate large networks.
Okay. Let me do a pause here, and let's discuss a little bit, like what Nick Matthew says here, and maybe let me start by asking you. So, what are the key points he's making? Like, what did you pick up from these 5-6 minutes?
That open source software is rising, and the technology that is used is based on this idea, and that it's programmed in Linux. That's what I get.
Okay, open source software on the rise. And this was unthinkable for like networking devices in the past, like 5-6 years ago, and now everybody, according to Nick Matthew, is and actually it's true, is working on this. Related to this, is open source software rising alone, or there are also some other developments that are happening and they go hand in hand with this? What did he say?
I think it was about the hardware that goes hand in hand with the software.
Right.
And he meant the switches that are fixed in that way that the equipment that is inside can be programmed. And you have the software to do it, you have to have the hardware as well.
Precisely. So he said that this open source software is on the rise, and this is hand in hand with programmable hardware. Which is also on the rise. Okay. This was the first, he had 3 bullets. This was the first bullet. This was the second bullet. How did he call this programmable hardware? Did he use also another term to refer to it? So this term also in the in last lecture in the slide, he also called it merchant silicon. He also called this merchant silicon or bare metal switches. Does anyone have a rough idea of what are these bare metal switches? Yes, Tolda.
I think like a net of devices that you can do, or you can program them to do anything that only the hardware part. This one, the switches for any applications.
Yes, it's right. It's mostly right. It's mostly right. Yes.
Isn't the switch we were talking about in the last lecture? The top of the rack, the server, the kind of server switch we were talking about, with a chip, with a RAM, with the CPU. Isn't that?
Yes, there are these switches, and these are chip usually. Chip switches that they have the basic hardware. Okay, and they are also analog. He also he said unlogoed, without a logo. Okay, it's like no-name switches, basically. No-name switches, cheap no-name switches, and which you can take and program the way you like. So these are also on the rise. Yes?
But the controller shouldn't be a very good server. Our computer only handles one packet for every flow, but it may need thousands or millions of packets for a big network. A good computer, fast processing computer.
True, yes.
So the value that the money that we don't spend on switch, doesn't we spend it on the controller eventually?
Leonida? Michalis, okay. Michal, I think the servers are cheaper in general. Today you can buy a good server, for few.
It depends on what you need. But,
yes, it depends on what you need. But remember, switches, good switches can cost in the order of hundreds. One switch can cost in the order, especially in the past, in the hundreds of thousands of dollars.
okay.
So I think you don't spend that much. You cannot give, 500,000 euros for a server. Yes, so these are it's relative terms. But let me come back here to the key points. Another key point. He said something about essential but not differentiating part. You remember this phrase? He said this a couple of times. He said something about the essential but not differentiating part of a service or of the operation. Does this ring a bell? Perhaps do you understand this? No? Okay, so basically the point made there was that open source software is used for the essential part of a service that a company provides, but not for the differentiating part of the service that a company provides. So in other words, this means that when I'm using open source software, so everybody is using the same software, everybody is using OpenStack, everybody is using open source software. So if my competitor is using the same software, I cannot differentiate from my competitor of, I'm selling, better service because I'm using the same software with him. And if I'm using also the same hardware with him, I cannot differentiate. So his point was that open source software is used for the essential part for the infrastructure. That's what he said. Open source software and the programmable chip hardware is used for the infrastructure, but not for the differentiating part. Not for the part that will give you the value-added services that will bring you the money in a company. Does this make sense now? And he pointed, like if you see like this figure here. So in this figure, I think, is it here? Yeah, I think it's over here. So, where is the differentiating part of the service that a company offers? Where is the differentiating part in this picture? Where is it sitting? What? Up, at the apps. Precisely, bravo. And here, if you cannot read this, I know, but on the very top it says proprietary software next to the apps. And there is the proprietary software that will bring you the differentiating part of the services you offer. Okay, so these are the key points so far.
Why do we care if an app, an application is a differentiating part? We care about the other stuff, the software and the hardware. Why do we care about the application? I mean that if I am a company and you are the competitive one and we use the same software and hardware, what do we care if another company makes an app on our equipment and can differentiate itself from other companies? That's what I can understand.
I also cannot understand fully the question, but if I get it correctly, we care how we will differentiate. If we use open source software as a company, we care how we will differentiate, what we will offer to our customers that is new and that will bring money at the end.
Okay.
Expression, I think, is gain a competitive advantage.
Okay, I'll start it from here. It's 3 minutes left.
There's a real struggle to find anybody that would do that.
Mm-hmm.
Now, it's like what we're all doing, right? It's what everyone is doing. It's the necessity for that essential but non-differentiating piece. What it means for those who operate on node networks is the creation of those rather small boxes at the top. Complicated. They're the differentiating pieces of proprietary software. And if anything, the biggest challenge that comes out of this is not the pieces here, because they're shaping up. The hard part is figuring out what are those proprietary luckily, for most of us, that's not our job. That's left for those that own and operate large networks. So what is it that's kind of going on in this sort of need? You'll have all seen the pictures before, but I want to repeat it. It sort of clarifies what's the sort of the problem facing the large network operator. The traffic is growing at 40 to 50% per year, right? Depends on who you ask and how you count. My monthly bill is not changing, and if it is changing, it's going down, not up. Therefore, the cost of ownership has to reduce by 40 to 50% per year. But in practice, depending again on who you ask, it seems to be reducing by about 20% per gigabit per second per year, i.e., margin is closing at about 20%. You've all seen this picture. I've seen this from, I think it's 7 different operators now. Numbers on, except for $30 a month. Revenue, again, slightly going down. Growth in traffic going up like this. The total cost per gigabit per second is increasing. And therefore, there comes a point, is this, depending on who you ask, where is that point at which essentially the margin goes away? And so what do you do if you're faced with this problem? You've already got 3 choices. Right? One is you reduce capital cost to try and reduce that cost per gigabit per second. Move to simpler hardware or an open source control plane is one example. Right? I think, again, that's partly why we're here. Reduce operational cost, which is once you've done that, throw out all the features you don't need so you don't have to support them. Focus the effort on supporting those features that you need. So you streamline the protocols, features, and software. Throw out stuff that you don't need. And then you increase the price. How do you increase the price? You increase the price by providing a different service to you from your competitors. So AT&T and Verizon, if they're trying to sell the same service to the US government, they have to do it off the same services, off the same IETF-defined services on the same boxes. You can't differentiate. If you own the software and can define the software, it gives you ability to define new proprietary services. We all win. We all win because the service gets better. So in the end, it's all in service of this. And if we can make this happen, the differentiated services to allow them to be more profitable in the same business, we all benefit. So the
Okay, so this is all for today. You can watch the rest of the video if you want offline on your own. Let's see now, let's discuss a little bit the last 3 minutes, what the discussion was about. And I think this is an interesting discussion because almost everything that happens in technology in general, it's driven by economics. The changes that happen in technology, they're usually the results of economics, and it's important to understand the economics so as to understand the ongoing changes and also to anticipate future changes. Now in these 2-3 slides, he discussed the economic situation that internet service providers like AT&T and Verizon in the United States are facing. Just maybe to repeat a little bit what he said, so as to make sure that we get this. So he started with this slide, right? So here he says, first of all, that the IP traffic, the internet traffic, increases every year 40-50%. Why is that? Because we all use more photos, more video, more YouTube, online streaming, so on, so on. Okay, and devices. What?
More devices, basically.
Also, more devices. However, we all pay the same, huh? Like, has your hotel or SITA bill changed the last 5-6 years? Things in your... Nice, yeah.
Well, it's kind of cheaper now. I mean, 5 years ago, maybe internet was about 30 euros, or now you can just have internet with 15 euros per month.
Exactly, right. So this is what is the yellow line here. It says that it's the same, or it gets even a little bit down. But the traffic grows. This means that also that when the traffic grows, also the cost of the internet service provider grow, because they need bigger routers, they need more routers, and also more operational expenses. So what he's saying here is that there will be a point, but because the costs for internet service providers increase and their revenues do not increase substantially, they even decrease, there will be a point that the margins, so they won't make any money, the margins will diminish. And these companies are facing this problem. So, and his point is that when you are facing with this problem, there are three things you can do, and this is what he's explaining here. So, if you are facing this problem, there are three things you can do. The first thing you can do is to reduce the capital expenses. What are the capital expenses? The expenses for infrastructure. Okay. And what does this mean? That you have to move to simpler hardware and open source control plane. Okay, instead of buying expensive switches and routers that cost a lot of money, you have to go to very simple hardware, cheap hardware, and open source control that controls this out. So this is the way to reduce the control plane, to reduce the capital expenses. Then he's saying that second, it's important to also reduce the operational expenses. So the expenses for the administrators that are managing and running the network. And this means that the management, the configuration and management of the network needs to become more simple. Okay, more simple management, lower cost of operation. And second, and finally, you need to increase the price. And here he clarified that with increasing the price, he meant not increasing the price of the baseline service that we all get, but increasing the price for value-added service, like, I don't know, OTTV or things that you buy on top, and that differentiate your network. And this will be done with, he argues, with proprietary software. Any comments? Something that you, yeah.
Basically, you are a big ISP, and you have some routers, some switches, and stuff like that. Let's say by Cisco. Now that you have something, it works. If it stops working for a reason, you can blame Cisco. Something open source and unbranded. If it stops working, it's your fault. So, may reduce capital cost, but when you do that, you get the risk higher for your company, because open source you are not 100% sure that it works, but from Cisco they make you believe that it has to work. It works, so you are a little bit more sure that, okay, I bought this switch.
Yes, but how will you differentiate when you don't take any risks? That's the thing.
That's for the app layer, I'm talking about the network layer now. In the network, you need to be sure that, okay, I'm an ISP, I have a lot of traffic going from me. I need to deliver every time for every packet, and I need to know that there is not a bug in my open source program, so something may collapse or may stop working.
Dimitri.
Χάρη. Δεν θέλω να το αναπώ μου τώρα.
Getting closer. Sorry. Michael, I remember it now. I think that's a good. It's a good counter argument. I think many people think they would argue something like that, and it's a valid argument. I mean, and some people, because of this, they wouldn't go down, wouldn't follow this path.
Yes, because I understand it in a small company that doesn't need redundancy so much, but if you are a big company like AT&T, you need to ensure that everything works fine.
Yeah, but here let me tell you though something. I didn't agree too much on the part you said about you need to trust the software. Why do you think the closed source software is better than the open source?
I don't, but I believe that if the closed source software collapses, you can blame the seller. So the seller needs to check it every time, needs to do something, and eventually, if his software destroys your network, he'll pay you. You can sue him. But in open source, if something collapses, okay, it's open source. There is a license that says.
Yeah. Okay, that's a good argument, but then you have. But there is a price for this, and the question is how big is the price tag?
The video says that in some point you stop getting paid. So AT&T at some point has to buy more expensive switches.
Yes.
And the price still stays the same. So
yes, but the buyers are increasing.
AT&T stopped getting paid.
Internet users today are not the same number as the internet user 5 years ago. So the price may be the same, but the users are increasing. So your income increasing as well. So you buy more expensive hardware because you have much more traffic, because you have much more users. So the price may be the same, but the users are lots of more.
Okay, so Michali, let's discuss in the break, or we can fight more about it. Then you tell me who wins. Okay, now let's switch to the next topic. So Nick McHugh talked about the importance of software and that everything as software will lead the world, basically. What he said precisely, and it's true that software becomes much more important in the context of computer networks. Now let me spend a few minutes to discuss something that is very important in the context of software, and that is the concept of abstractions. Okay, when we are software engineers, one of the first things we learn is that when we program, we need to do good abstractions. Okay, so how many of you know what is an abstraction?
In software.
Yes. So most of you do. Or not, few of you. Okay, let's discuss this. And let's start with a problem. When we have to engineer very complex systems, like the internet, or even, this is not just in computer networks or even in computer science, it's in everything, anything that you engineer. I mean, the streets of a city or anything you make, these are complex systems, very complex systems. And when you build, you design a complex system, there is a very important rule that you need to follow to engineer this correctly. And this rule says, break it down into tractable pieces. Okay, and identify abstractions. Abstractions, I will try to, I will explain it mostly by example because it's not very easy to define it strictly. Abstraction is precisely this process, is the process of getting a very complex system like a computer communication network for the global, for the entire world that we want to engineer, to build, and breaking this complex system into pieces, into different components. And this, the design and the selection of this component is called, involves abstractions. In Greek, abstractions means affaircy, that we hide, reduce the details. It means that in order to build such a system, we need to hide details so as the system is more manageable. Trust or not? Okay. So here is a definition of abstraction. So, software engineering, computer science. Okay. So it's you arrange complexity and you suppress details in the more lower level. And let's see this with a well-known example. So this is a definition of abstraction. Okay, the 5-level protocol stack, or even the 7-level protocol stack of OSI. These are abstractions. So when two applications, or when we write a network application, we don't need to know what physical level technology is used. And we don't need to know how to modulate the signal, the bits into signal. Okay, because this wouldn't work. So here you see also one principle of abstractions, that abstractions are usually built in layers. And lower layers, we have the highest detail component. But if we go up, we hide the details. Okay, so let me quickly do then a PI question that I have for us before we move on.
Σε αυτά τα τι Κάπως άλλη διαφήξεις.
Okay, so I will start in a random order. What do you say about identify components? Yes. Who says no? What do you say about easily update components?
Yes.
I think these are very clear. Simplify reasoning and debugging.
Yes.
And understanding too, it helps understand like the code.
But debugging isn't simple. Because you need, if you have a mistake in a higher class, to get every other component, so up there to find where the bug is, if you are not sure exactly what this component is. For this reason, I believe debugging is harder.
But if you don't use abstractions at all, imagine it would be a mess. I mean, it would be
Yes,
flat,
it will, but in debug mode, you know this line and okay, this is the third line.
hard to localize it.
Yes.
Not in Python. Python is undebuggable.
Okay. Better management. Yes. Better platform compatibility.
Yes.
Doesn't really have to do with platform compatibility. In the way I mean it here, Mac, Windows, this is usually a choice of the programming language.
So it's no.
It's no. Pure lines of code?
Yes.
Yes.
Yes. Everybody says yes, no? No. I mean, I could take it either way here about pure lines of code. Faster software?
No.
No?
Yes.
Says no. Says yes. Why yes? Tell me.
Because when you write in the small pieces, you get a better idea of what you're doing and what is going on, so you're gonna write better code instead of writing spaghetti code style.
I also believe that it will end up being better in faster software. I mean, one argument,
Abstraction.
but okay, say it, Michal.
Abstraction happens in runtime. So when you have an abstract class and some other class takes some attributes for a higher level class, it's not the linking. It's not happening in the compile time. It's happening in the runtime. So basically, it's not faster when we have to do with a compiler, when we have to do with an interpreter.
Michal, now I'm a bit confused with how exactly you mean abstraction. Do you mean here...
like C++, like interface and classes that inherits.
Yeah, but inheritance is different than abstraction, right?
Okay, I mean polymorphism and inheritance. In this way, I mean abstraction. Okay, it's not faster, but
So here I mean something more basic, that we have just some classes, maybe forget about inheritance.
yes, in this way,
Yeah.
it's fast. General way when we talk about abstraction.
Okay, so just to speed up a bit. Okay, yeah, I mean that's an interesting point. I could think that abstractions and modular software can help the speed because you could turn off some components of the software at runtime and some plugins and things like that, and therefore use only what you really need. And this could reduce also memory consumption and things like that. But it's not obvious, it's not precisely obvious if abstractions could help. I mean, one could argue the other way around, that abstractions might introduce some overhead and things like that. Let's tell you.
Just to make it clear, I think, let's talk about Firefox, for example. Firefox is a big piece of software, really big. It's open source and everything. And it works on the application layer, right? So everybody that's contributing to this project has to do only with the application layer. Now let's say that there was no abstractions, there were no layers, and that Mozilla Firefox had to deal with every layer up to the physical layer. So when you're programming, you have to think about how to modulate and demodulate the signals. Think how such a monstrous piece of software it would be. It would be, yeah. That's in this way. There's no discussion if you need that abstraction.
I meant abstraction like we use C++ in
yeah, but that's another thing.
Yes,
this
I
is not what
understand.
we're talking about.
So let's have a break. You can continue on the break. Okay, so let's slowly restart. We started discussing about abstractions. Okay. Next point. How do we find good abstractions? Find good abstractions. We identify reusable components. Okay, that's step number one. Then step number two, we hide under these reusable components the unnecessary details. In addition, we also define the relationships between the components. Okay. Think of, for example, the relationships in the protocol stack. We have explicit relationships between layer 2 and layer 3, layer 3 and layer 4, and so on. And these are also known as APIs, the APIs of the class. Okay. Okay, hiding, I think this is very clear. It's we hide away the details. I think this is like among the more challenging parts, the reusable components. And of course, abstractions are usually organized in layers, as we saw already. Okay, so now in the internet, as we know, we have, of course, the data plane, and we have on top of the data plane the control plane. In the data plane, we know the abstractions that have been defined for it. This is no other than the 5 levels of the protocol stack. However, if we look at the control plane, up to date, there does not exist a well-defined set of abstractions for the control plane of computer networks. Okay. So let's do this as an exercise now. So if we would like to control a computer network, let's think a little bit. How would we write a system that does that? So which abstractions shall we pick? Yeah.
I think we should identify every single piece of the network first and make it an abstraction. I mean, the switch would be an abstraction, the hub would be another one. And when you identify those, then you can start implementing them. Wasn't that the question? Abstract the control plane.
Yes.
You can have the whole network as one on top, one thing. We have to split it.
Mm-hmm.
And if you split the network, you get every component here to make a network, and that's our abstractions.
Yes.
Every single entity.
But let me. Okay, that's one thought. Any other thoughts? Maybe do you want to think about it for a minute? Let's say that you have this as an exercise. You are about to write a control plane for a computer network. What are the reusable components? Okay, so any thoughts?
Parts connecting with parts and shortest parts.
Okay, that's interesting. Though in data network, in datagram networks, the paths are not really strictly defined. Yeah. Do you see what I mean?
Yes, but what frequency? Okay, things. But there are some that will mostly.
Okay, paths. What are the functions? What does the control plane need to do?
Packet to the right path.
Every packet.
Right, control, yes. Control the packet, right?
Every packet, not just.
Every packet. something else. So we need to exercise control. So we need a way to a function that allows us to control the network. Right. Alex,
different rules for different packets is kind of.
Yes, I think this. So you are saying abstract, like having some sort of reusable rules. Okay. Correct. But let's backtrack here. So what is the job of the control plane? So we said that it needs to control how packets are routed, but it needs to do something more. What does it need to do in order to exercise control? Oh, yeah. Olga?
Just implement some rule function. For example, packet arrive at network devices.
Okay.
So basically
so
the
two
process.
different points here. So Michael says, no, what did you say?
No, what's in the
Correct. So basically you're saying more or less the same thing, that we need to have some rules, know what we want to do with the packet, right? This in the context of software-defined networks, they call policies usually. What is the policy of the network? What do we want to do? But here, there is something that we haven't stated. It's very fundamental. What do we need when we exercise control on something? Oh, what do we need to know? Yes, all the components. We need to know all the components. And what else?
They're connected to each other.
How they are connected, precisely. What else?
What is the purpose of the network?
Okay, this is on the rules, on the policy side. But yeah, so basically this is what I need. We need to know what are the components and what is the state. So when we control an infrastructure, we need at every point in time to know the state of this infrastructure. And if this is a computer network, we need to know the state of the computer network in order to control it. So basically, we have stated three things. We need so basically the state. We need a way to control it. We need a bunch of rules or policies that will define how we will control it. These three things. Okay. So if we missed something, so basically it's these three things. Learn the network state, the topology, decide how to configure it. So this is the rules, the policies. And push the configuration to network elements. So these are the three. And in these three processes, we have some reusability, and what is reusable is the network topology and the state. I mean, every time we need to control a network, we will need to know what is the network topology, what is the state of the network, and we need a way to push configuration to network elements. Okay, so a way of understanding and of viewing software-defined networks is precisely in terms of these abstractions. It's basically we have two plus one abstractions in software-defined networks. The first is the definition of a way to push configuration to the network, and this is the OpenFlow network. The OpenFlow, for example, is one way to do that. So we have the controller that is also called the network operating system, and then over the controller needs to have a graph, needs to maintain a graph that is the topology of the network, and over the controller we have a control program that decides how we route packets. Okay. So here we have two abstractions. The first is the so-called the forwarding abstraction, that is basically over here, and then is the network abstraction that is over here. And today I'm going to spend the next 30 minutes to discuss a little bit more about this network graph abstraction. Okay. So, I think you know this. Just notice that these abstractions are again organized in layers. Okay, we have the bottom layer, the second layer, and the third layer. And here we can introduce one more abstraction, that is the network hypervisor. Network hypervisor is one more possible abstraction that sits on top of the network operating system and that creates abstract views of the topology. Here you can think of this, that it is analogous to the hypervisor we have in operating systems. There the hypervisor abstracts away the physical level details of a computer, the memory, the CPU, and provides like a virtual view on top. And the network hypervisor does the equivalent in the context of computer networks. It abstracts away the topology, the hardware of the switches and the CPU, they have the memory resources and so on, and it can provide virtual networks on top of a physical network. So before I move on, do you have any question in this part? Yes, Alex.
I don't understand fully what hypervisor. Why should we have an assumption that it's away?
Did you understand the description that it provides virtual networks, essentially? These are useful data centers, for example. Maybe today it's not, we'll have a separate lecture about this, but let me briefly give you an idea. In data centers, sometimes within a data center, you have the same tenant. Okay, let's say the University of Crete is a tenant of the data center of Amazon, and we rent there to thousands or hundreds of computers. And we might want to control the network in the data center because of, I don't know, we want to have some firewalls or some intrusion detection systems or some caching that happens in the network. Of course, Amazon wouldn't like to give us control of the entire network of Amazon, of the data center, but it could expose us some virtual network that is on between our virtual machines, and that where we could have some level of control on the virtual network, but not on the entire network or on the physical network. Okay. But it's a topic we will discuss again. So, what I would like to keep from the second part of the lecture is the concept of abstractions that is important. That by trying in software, when we talk about software, and that one way to view software-defined networking in terms of the three layers we saw before is that SDN introduces a set of abstractions for the control plane of networks. Equivalently, as we have the 5-level layer of abstractions for the data plane of networks. This is one way to reason, and actually this is precisely the way the creators of SDN explained SDN when it first began. Any questions? Okay, now let's spend the next 40 minutes to discuss about, in the previous slide, the central component, that is the controller. What is the job of the controller? To maintain an up-to-date view of the network state, to configure network elements, and to provide a graph or some abstraction to the applications on top that is known as the northbound interface. So if now we would like to build a controller, here are some of the challenges that we would face. How does it scale to large networks? How do we deal with failures? How do we make sure that it runs fast? And how do we design a northbound API that is general and simple for application programmers to use. These are some of the challenges. Some of them are still open. There are topics of research in the area of software-defined networks. Especially here on the bottom, there is lots of work going on. Okay, and we will discuss next about some controllers that exist today. We will see first the first generation controllers, and briefly, very briefly, the second generation controllers, for which we will revisit in one of the future lectures. Here is a list. I'm sure this is not a complete list. There are dozens of controllers today, and there is lots of activity going on in the community. We have Nox, Box, Reu, Floodlight, Open Daylight. Are you familiar with anyone here? Box. Do you know any other than Box?
I don't even know Box.
That's not. Not yet, you mean, huh?
We don't get no.
So the controllers differ, of course, first of all, in the language that is used to write applications on top of them. Second, they differ in terms of the features they provide to the users. Some of them focus on the southbound API, and they support more protocols, for example, not just OpenFlow, but also OVSDB, netconf, and other protocols that could be used to control network hardware and devices. Some other focus on the northbound interface, and there they also support have richer features for the northbound interface. Other are integrated with OpenStack, that is a very popular virtual machine management software that is used in data centers a lot today. Of course, they also diversify with respect to their purpose, especially the first generation of controllers includes several that were designed just by students as part of their research, and they are not really production controllers. In contrast, the second generation of controllers, ONOS, and Open Daylight in particular, they are systems that are targeting operational networks and real internet service providers and so on, and data centers and so on. Of course, we can diversify the controllers with respect to how difficult they are to learn them, as well as to the user community, how many users they have. Okay, now one of the very first, probably the first controller historically was the Nox controller, which is open source. It supports only OpenFlow 1.0. and it's an event-driven controller. Okay, so this means that the controller registers for event, and programmers write event handlers that when a specific event comes, a link failure, a packeting event, we decide how we will handle the event. Okay, so here is a simplified view of what sits inside the controller. On the right, and this is common in every controller, we have a database that stores a view of the topology. Okay, here it's called the network view. In some other controllers, it is called the network information base, and so on. In all cases, this is what basically it's also the topology, so the network abstraction, what we call the network abstraction in the slides we saw before. Okay, we have here support and implementation of OpenFlow, and as we saw, it uses an event-based model. This means that when we have a new switch, a packet in, and so on, we write a control program that responds to this event and takes actions accordingly. Which controller do you think is the most related to Knox? Fox. Okay, fantastic. I think you are right. So while Knox is written in okay, here. So basically, here is some more information on what is in the network view. So it's the topology. Also, in addition to the topology, we have the hosts. And users, and the location of users, and something that is not in the network view is the traffic, the volume of traffic we have in the network. So Knox is a controller that has fairly good performance, and it's also fairly general because of the event-based model. However, it's fairly simple, so in terms of robustness, it might not be the best one. And it also has, as I said, the good simplicity. Okay, Fox is the Python version of Knox. It's also one of the very first controllers, and it is used for educational purposes. It's usually the very first controller that someone starts with in SDN. It uses OpenFlow 1.0, the first version of OpenFlow, and it's fairly widely used. Basically, in most universities, they use POX to start with OpenFlow. It's fairly easy to write beginners programs. However, it's not very it doesn't have very good performance. Okay, after POX and Knox, one of the first, more mature controllers, still in the first generation of controllers, was Onyx. Onyx is documented in this paper, and it's very well known. It's probably the most well-known controller in the scientific community, in the academic community, because it was the first controller that led to a decent long paper that describes in detail the various challenges involved in building it, and this is extremely highly cited today. So Onyx has almost 800 citations, and it's a paper, just from a few years ago, which is remarkable. So it's one of the, if you are interested in doing research here, it's one of the first papers you have to study. On the other side, Onyx is still, it's not something comprehensive or extremely sophisticated, but it does solve some interesting problems. And this is basically the part that it solves. It's the first controller that was distributed. Okay. In Nox and POX, we have a single controller for the entire network. Here we have a distributed controller. And this helps deal with scalability and helps deal with robustness in the case of failures. Onyx, however, is we just know the paper. We know nothing more about it. There is no code available for Onyx. It's closed source. In contrast to Nox and POX, and also in contrast to most other controllers. And there are some speculations that initially in the Google network, that was the first network that adopted SDN, Onyx was used as a controller there. But this is not officially stated by Google, but it's speculations that this was used as Google was involved in this scientific publication. Okay, here you see another view of the well-known diagram of layers. It's basically more or less the same. South API, North API. The only difference is here that we have multiple controllers, and we have software that we speak with other controllers. Remember that this is called South, this is called North. What's the name for this? Who can imagine?
Bridge.
How?
Bridge.
No? Here it's called the East-West interface. Okay, so this is called the East-West interface in the middle. Okay, so here are the information we store in the network information base. This is it's pretty straightforward, and in every similar network view or network information base, we store the topology as well as some metadata about the network topology. And what are these metadata? Here we have, for example, for each node in the network, we have information about the ports of the switches. Okay, so what's the capacity, for example, of the switch, of each port, which switches are up, which switches are down, and also other features that can be useful here. And so on. We have links, we have hosts, forwarding tables, and so on. Okay, to support greater scalability, the Onyx controller, and this is one of the interesting features of this controller, enables to partition a network. So a network, we can partition it, and in different parts of the network we have a separate controller. Okay. In this case, an instance of the controller keeps a subset of the network information base. So a partial view of the network. Furthermore, according to the paper, it provides support for aggregation, which means that the details of subsets of the network are hidden from other controllers. And when we have redundant controllers that we need to synchronize, it provides a storage that is called that maintains consistency, like in Dropbox, for example, between different instances of the database in the two controllers. Any questions? Oh, it's almost 4 o'clock, huh? Okay. Good. Okay, see these slides on your own. It's basically an example about consistency. Then Ryu. Ryu is a newer controller than POX. It's also written in Python, but in contrast to POX, which is just supports OpenFlow 1.0, and it hasn't been updated since then. Ryu is an up-to-date controller. It supports the latest versions of OpenFlow, and it also supports other southbound APIs. However, it's written in Python, so it's not very good in terms of performance. Another well-known controller is Floodlight. Floodlight was developed by one of the early startups in the area of software-defined networks. It was developed by Big Switch. That's the name of the startup, Big Switch Networks. It's a Java controller. This is also open source. It is used in production networks. However, it's very difficult to learn it. Like I remember in the past an assignment in Floodlight, and some students they hated it. They just hated it. But since then, it might have improved a lot. And it has a number of features. It's basically one of the well-known controllers. It has integration with OpenStack, a REST API on the north, and so on. Okay, so this is for the first generation of controllers. And let me close this lecture with a couple of words about Open Daylight. So today we have a second generation of controllers, and basically this is where all the activities is going on today. These are really big projects with lots of support by a community that is engaged around it. So the one project is called Open Daylight, and it has been started by the Linux Foundation, and the vision there is to build a Linux for computer networks, this is just an analogy. So, and this Linux is called Open Daylight. Open Daylight is a pretty big project. It has lots of support from the industry and a very big community around it. Here are the first 3 releases of Open Daylight, hydrogen, helium, and lithium, but there is also a newer release after lithium. It started like that. The lithium release has really many components. It's a huge project. It has many projects and many support for many different protocols here. So if you want to read more about it, you can do it on your own. So it's an industry-backed effort to develop a broader set of SDN solutions. It is not just OpenFlow. It's many more protocols than OpenFlow, but it's also something that is difficult to start using. It takes time to learn it. It has a little bit steep learning curve. Okay, and finally we have the other second generation controller. It's called ONOS, Open Network Operating System. This is a project that has been started by Stanford. It's the same team that developed OpenFlow. They also work a lot on establishing a great community, a big community around them. These are projects that are like these days are very active projects, and that these days are like these years are important because the Linux of computer networks are being built, let's say, are in progress of being built. That's the vision. And we will have another lecture about ONOS, like in one of the future lectures, Lefteris will tell us some things about ONOS and the latest developments about it. Okay, so some pointers for further reading, and that's all for today.